changed the way humans produce things. The step into production technology, which was completely different from the past, is also called the Industrial Revolution. The first Industrial Revolution began in 18th century using steam power and mechanization of production. The second Industrial Revolution began in the 19th century through the discovery of electricity assembly line production. The third Industrial Revolution began in the 20th century through partial automation using memory, programmable controls, and computers. We are currently implementing the fourth industrial revolution. This is characterized by the application of information and communication technology to industry and is also known as Industry 4.0. It builds on the development of the third industrial revolution. Production systems that already have computer technology are expanded by network connection and have a digital twin on the internet, so to speak. A very good morning to one and all. I, Dr. Sachin Agrawal, welcome you all on the behalf of Department of Mechanical Engineering, Devgiri Institute of Engineering and Management Studies, Aurangabad, for the technical session. DIMS has been an institute in Marathwada which imparts best of the technical, professional and life skills to its students since 2009. We are NAC A graded, accredited and ISO 9001 2015 certified institute. Times Engineering 2021 survey honored us with ranking for our endeavor in providing career opportunities to students through our excellent academics and industrial practices amongst all the private engineering institutes from Marathwada region. Today only Times of India Research Methodology column rank us 127 in their list. We are committed to develop right kind of attitude, knowledge, skills which will help students to serve the nation in a progressive way, and such technical sessions support this to a great extent, where eminent speakers make the students aware about the latest development in technologies across the globe. For this session, we have such a distinguished personality, Mr. Ajay Deshkar, with us. Heartiest welcome to you, sir. I also welcome Mr. Sachin Chittanand and Rishikesh Kolapkar from 3D Engineering Automation LLP Pune. I take this opportunity to honor the presence of Dr. Ullas Shiurkar sir, Director DIMS. I gratify the presence of Head of the Department Mechanical, Professor PG Taur sir, Head of the Department Computer Science and Engineering, Professor SB Kalyankar sir, Head of the Department Electronics and Communication Engineering, Dr. RM Auti sir, faculty members and students on this occasion. Welcome all. According to Warren Bennis, a pioneer in the field of modern day leadership studies, leadership is the capacity to translate vision into reality. This comes real with Dr. Ullas Shiurkar sir, who is the director of DIMS since its inception. The institute has grown substantially with his leadership and is now one of the finest when it comes to academics, discipline and placements in Marathwada. An edupreneur, a recognized PhD guide, author of many books, member of Academic Council of Dr. Batu Lonere and past active member on various committee of Dr. Bamu Aurangabad. Sir is in the field of education since last 33 years. Our parent trust MSP Mandal gave him Seva Gaurav Award in 2014 for his exceptional services to the institute. Rotary Club Aurangabad honored him with Guruvarya Award in 2011. The next year, he was delineated Dronacharya Award from Lions Club Aurangabad. Having such an able leadership is always truly inspirational for all of us. Now I request Dr. Shiurkar sir to address us. Sir.
Thank you, Sachin. My friend, old friend, basically we can call because we are basically from Aurangabad, myself and Ajay. There was some informal discussion with Ajay regarding some or other issues after a very long period. And immediately I requested him to be with us. Actually, I requested him for offline mode, but what he says, यार चिंता नको करू मी ऑनलाईन सुद्धा चांगलं घेतो. And I know head of the department, Taur sir, Kalyankar, Thunge, Auti sir, Gandhi sir, my young friends. As Sachin has narrated, Industry 4.0 is going to be a key role, going to play the key role in the industrial development, not in Aurangabad, not in India, but throughout the globe. Even some of the countries are talking about Industry 5.0. And very frankly speaking, the syllabus, what we are teaching, is not changing so fastly. There are the limitations. Therefore, I requested Ajay to talk with our faculty. Because as a teacher, what we are doing, we are teaching them what is in the syllabus, but that is a compulsion part. But if we go beyond the syllabus, it is going to be benefited to the students. And I know my team is very strong. We are already working on this. Some or other faculty are doing certain projects. Even Ajay, I can tell you, we are conducting one project competition for my teachers only.
Okay.
Every department has submitted minimum 3 projects. And one fantastic project is the outcome. It is from mechanical department. Existing CT scan machine can be used for the mammography also. Normally, cost of CT scan machine 2.5 crores, mammography is 1 crore rupees. Just developing the software and one fixture, we can use the CT scan machine for this. This is a very good outcome of our hackathon project.
Okay.
What is my plus point, Ajay? My faculty is young. They want to do something. And definitely, what I request you, Ajay, to be with us, not for as online. Whenever you're in Aurangabad, do visit the college, conduct a meeting with our faculty. After all, everybody has to go beyond. As an industry, you have certain responsibility. As an educationalist, we have certain responsibility. The combination of 3D engineering and DMGRI is going to play a very important role for the development of the students. So thank you once again. Thank you. Over to you, Sachin.
Thank you very much, sir. Before requesting Mr. Deshkar sir to start the session, I would like to introduce him. Ajay Deshkar is currently the CEO of 3D Engineering Automation LLP Pune. He has expertise in manufacturing, engineering and product and tool and design. Sir graduated in mechanical engineering from Government College of Engineering Aurangabad in 1987. He postgraduated in tool engineering from Tool Room and Training Center, Delhi in the year 1989. In his current profile, he leads implementation of engineering solutions from Siemens PLM, ANSYS and EOS GmbH to manufacturing industries in India. The technologies that Ajay sir and his company delivers are design and digital manufacturing solutions, mechanical, structural and fluid simulation solutions and services, virtual reality solutions and additive manufacturing of plastic and metals. Earlier to this, he co-founded the engineering division of Expert Group in 1999, of which he was a member board for 15 years and headed design and development of tools and SPMs in his manufacturing venture, Paramount Tools, for 10 years. Sir has presented technology papers in international summits and has managed design, automation and PLM projects for clients in Europe, US and India. He is a consultant to many manufacturing companies in India. His hobbies are music and graphic design. Key achievements in his professional journeys are as displaying leadership and heading initiatives of engineering solution into a higher orbit, manage engineering solution delivery to international clients. In the process, he traveled to US, UK, Sweden, Germany, Netherlands, South Africa, Malaysia and China. Presented technical papers on design, automation and PLM in different forums like Solid Edge Global Summit at Atlanta, USA, Asia Pacific meets in Malaysia and China, national and international meets at Siemens PLM. chief architect of several technology implementation projects in industry sector involving design automation projects for knowledge management through CAD customization, product and process digitization and simulation, IoT and Industry 4.0. Manage large projects of PDM and PLM implementation. Council recruited, mentor, train over 2,500 students and engineering professional as a hobby and as a part of his profession. Engage in active education services through visiting faculty at engineering colleges, through seminars to education sector and within the training activity of the organization. Design and manufacture over 150 plus special purpose machines delivered to auto OEMs and suppliers, machinery manufacturers, pharmaceutical companies, and consumable durables. Designed and manufactured several tools delivered to auto suppliers, pharmaceutical companies, and consumable durable manufacturers. Lead implementation of e-manufacturing using metal 3D printing in commercial and government organization of repute. Such a committed person in the field of product and process digitization and simulation, IoT and Industry 4.0 we are having today with us. I request Mr. Ajay Deshkar sir to begin the session. Before that, I request all faculties and students to pose their questions in the chat box. Over to you, sir.
Thank you so much, Mr. Sachin. That was too much of a introduction. I had not planned planned it to be so much. I'm just a student forever, and at this moment, I can only thank Ullas sir for giving me this opportunity. And I'm very sure that this is a beginning of a long association. Like Ullas mentioned, I would definitely have a continuous association where we can have certain projects together. With this background, let me, Ullas, allow to present my case in the sense that I would like to start up with a presentation which I had designed some time back for our own college. And let me know once you can see the screen.
Yes, sir, it's visible.
It's visible. Okay, fantastic. So, good morning, everyone, again, and thank you for the introductions to begin with. Thank you for having me here today for this session, which was about digitization in product development and manufacturing. And while we talk about this, I would definitely want this session. I'll take a little bit of breaks between three sections and invite questions between them if you all have them. And I would definitely be available over any email or phone communication after this session as well to answer your questions. This presentation is going to encompass a lot of technology, so it is not really possible to answer all the questions together at one point. So we can extend this session over smaller sessions later. But to begin with, let me start off with a collage which I had started off making. And this collage which I had designed actually starts from a concept level where you have concepts and sketches being done for a product. Which converts into CAD. So in the good old days when me or Ullas also became engineers, we were doing these drawings on the paper. And when even I did my post-graduation, that was on tracing sheets and blueprints, from where we went into CAD and computer-aided designing using various technologies, started making product design even more compelling, in the sense that we started making products which were more usable, more affordable, optimized, as well as lightweighted. All of these things were possible primarily because of a lot of simulation. And during this simulation, one of the important facts that we need to realize is simulation is nothing but virtual prototyping. And this prototyping primarily gives you all those field level, what you can say, functional stresses that a component can go through or a product can go through. And these could include mechanical fluid stresses, magnetic stresses, and things like that. You can imagine trying to prototype physically an aeroplane and allowing it to fly without the simulation and trying to see if it flies, it's okay. If it falls down, then let's redesign it sometime later again. That's not how design happens. So virtual prototyping through use of simulation has been one of the very important aspects for a long time. Once you have the entire tool design done, once you have the entire product design done, today we have what you can say a flat world where things happen across the world. The design happens somewhere in India, the manufacturing can happen somewhere in China, the company IP is held somewhere in Germany, let's say. And in such a manner, when the product is being designed, virtual reality takes a very important place into the entire design process. So that's the first phase where you like to do the product designing. Once the product is made and if it is to be mass produced, you go into the process definition. And then you first define what kind of process it will take. You design the machinery, the tools that are required to make the components, and then do the plant simulation or the machine simulation itself. You prepare a batch out of it. And then during all of these processes, you understand whether the process is rightly made or not. So you have a digital process created, and that digital process, once established, you go into the mass production. Initial batches confirmed, then you go into the ramp up of the production. During the production, you have a control plan, you go into the quality plan, you do planning and scheduling, and then come out with a process that can measure the performance of the production perfectly well. And then you go into the smart manufacturing in a connected factory, which allows a lot of other technologies to connect with, such as IoT, which is nothing but tools required for connecting the factories, as well as artificial intelligence and machine learning, etc. And all of this is possible primarily because of digitization. And this one image primarily allows us to go through the entire status of the agenda that we have today, which is product and manufacturing and product and process and performance digitization. So I have made this image and split this into three parts. And as you can see on the image, I have distributed this into three parts. The first part is about the product. The second part is about the process, and the third part is about the performance or the manufacturing performance. So these three segments we are going to cover today. There is a lot to be covered. And I can tell you that today we have allocated about 75 minutes for this discussion. So if I am getting a 60-minute slot of this discussion, I can have 60-minute slot or even more slots for individual components, as you can see here, and make sure that justice is given to each topic here on. So with this small introduction of the topic today, let me start into the first activity or the first activity of an entire value chain, which starts from the concept and we come to what is called as a product development. So the first part, can you hear the sound of the presentation, please?
Yes, sir.
So this graphic will tell you how parts are produced, how they are imagined, how they can speak towards the activity part of it. Digital enterprise where you have the entire suite of industries connected together. And you can see here there is a design environment, there is a planning environment, and the manufacturing together, all into a single digital enterprise, which will get connected together into a single environment. So we come to the first part, which is about the product development itself. And when we say product development, we're talking about creating a sketch of a product, making iterations, making varieties of products or iterations of the product, making sketches of those iterations, making them more friendly by using CAD. And then once the CAD is ready, what we are going to do is we are going to simulate the CAD which is there. So designing is all about the computer aided designing. Today, I don't have to fortunately tell what it is about because I remember the first time we are running this organization called 3D Engineering, and the first time when I was in one of the colleges where I started making a demonstration of 3D parts by using CAD. I would not believe my ears when I saw people clapping when I created a 3D model out of 2D sketches, because I felt that this is what the tool is made about, and people were considering that as a magic, which today, fortunately, has been accepted as the standard way of documentation of designs all across industry, may it be small or large. Once the design is ready, you go into simulation of those products. And that simulation can include a mechanical structural simulation, fluid simulation, electromagnetic simulation, thermal simulation, and vibration, impact, durability, and all of those simulations coming through. We're going to see a little bit of this today in the session. And as I said, I can go into a deeper session by having individual sessions each on product development and process development. One of the important aspects today, because of the advent of prototyping, is also because of creating 3D printed parts. In the good old days, carpentry, blacksmithy, and such traditional manufacturing technologies were used to create prototypes. And these prototypes that were created were then tested either only for the fit and function or the ergonomics of it. Whereas today you can have printed parts in the material that you want them to be. So there could be a variety of plastics, which could include thermoplastics of polyamides and parts which are such as ABS and things like that, which are actually the standard products which are made by injection molding as a technology. And then you have metal parts which could be made into aluminum, titanium, cobalt, chromium, die steel even. And then all of these parts can be put to functional use by making sure that these parts are ready. And before the mass production, they are prototyped and tested for their ultimate function. So this entire product development cycle, which includes the CAD part, the product design part, simulation and prototyping together. And I talked about virtual reality, allowing people to wear goggles and seated on their chairs, they can actually have an entire machinery being reviewed across geographies. So 3 people seated at 3 different continents can be actually seated in front of a machine where one can demonstrate by opening maybe the cover of a machine and then showing the internal parts, and the other person asking questions about the parts inside it and things like that. So that's how much virtual reality can be put to use, and I will be very pleased to have any of these demonstrations done to you from the team that we have. And with this, I go a little bit deeper into what all technologies are used to this. So we start with the concept and CAD, where today, irrespective of the CAD manufacturer or the IP that is created by many companies, have solutions for industrial designing, where you start with the concept or reverse engineer things. From there, you have packaging design, mechanical design, electromagnetic mechanical designs, as well as mechatronics concept design. You go into the concept styling to begin with, then do the packaging. You create class A surfaces, and the component level and assembly level designs are happening. Today, none of the mechanical designs would be complete without having electrical or electronics into it. So we have electrical routing and electronics embedded into it, even software for that matter. So all of this together create the entire product design, if you like, may it be a single part or an assembly to help you create the CAD. I am very sure that most of the people here in this session would be completely aware about how this works. A detailed session can be worked on this, but then I'm not going to dwell too much onto the CAD part, because that's something which is more or less converted into a documentation style today. And what used to be earlier is the last box in this segment, which is called as the drawings, which are the 2D drawings printed on a sheet of paper, which still remain a part of some of the manufacturing facilities within India. So India is a very peculiar state where leave aside the first industrial revolution, but the second, third, and the fourth industrial revolution stay together. And there are single factories where all of these revolutions can be used together at one point in time. So we go into the next step where we see various types of simulations. And these simulations could be mechanical, structural, where you can put the actual stress and you can, the stress strain diagram, which was typically studied during the engineering days, can be put to use. We have rigid body dynamics where we can have parts moving together and the dynamics or the kinematics within it can be put into motion. We have explicit dynamics which could include parts falling down and creating an impact. So explicit dynamics of parts and having other parts into it. Parts which are done through shock and you can see here something piercing into a body. So such impacts can be now analyzed. So all of these analyses are actually the way the parts are designed and now put to use into the physical world. We have other simulations such as the crash simulation. We have seen car crash in many advertisements as well, and making sure that the passengers inside the car or any other structure are safe while this crash is happening. So there are crash simulations which also happen. Then there are simulations which can be into fluids. So a lot of steam, air, liquids can flow through, and you have a lot of stresses being induced because of the fluid flow. This fluid flow could be change in the state from liquid to gaseous state, and all of these together can make sure that the ample stresses are put onto the physical body, and that can be analyzed through this, because you can realize how much aerospace component or a missile or even a ship for that matter going into water or air can actually go through such kind of simulations. Then there is low frequency simulation of the Maxwell equations which are done in motors, etc. High frequency simulations. This is one very important aspect and a very deep level study initially. And let me tell you, I was a strong opposer of computer aided design and simulation at the start of my career. A little bit well educated, should I say, but a little bit high headed as well at that time, when I realized that everything, I had thought that everything was in my mind and in my hands. The skill of design was in my hands, and no computers would actually be able to replace that. And honestly, at that time, about 30 years back, these technologies were really at the concept level. But now, as we start making a car design or maybe any other mechanical assembly or a machine design, you'll realize that a car can have as many as 20 odd high frequency antennas. So there can be a Bluetooth antenna, there could be a radio frequency antenna, there can be a GPS which is there into the car, and several other such antennas. And these antennas are actually creating a space or a bubble which can be interfering with each other and giving you a very low signal integrity. And because of all of this, it is important to place these antennas at the proper place in a particular vehicle. So let's start talking about the car itself as a vehicle. And in that, all of these need to be placed such a manner that all of these do not interfere with each other, and the signal integrity is perfectly all right, so that all of these can deliver the required function that they are. Notwithstanding that, there is also a value of these high frequencies stresses that come up into an antenna to give you heat. So you need to position a mechanism to have a proper flow. As we speak, I'm talking from a laptop, and it may have a fan, or a computer may have a fan to make sure that the heated circuit boards, because of the frequency that they run on, need to be cooled down for proper performance. So you have a radio frequency which creates heat, and that heat needs to be further what you can say cooled down using ice pack as a solution. So there are all of these simulations possible now. And these are all virtually possible to make sure that the product that we need to design finally comes to fruition, and it becomes a product which is safe, which is at the same time functional and long lasting and durable. So all of these come together and make sure that the design or the product design becomes robust. There are various other technologies which are there, such as subtractive manufacturing. We have seen all of these happening from subtractive manufacturing, and additive manufacturing is now taking its own place into product design. And as you can see, to create a sphere, there are two different technologies here. The subtractive manufacturing is the one which is removing material from a block or an ingot to give a net shape. And in additive, you are creating a part ground up layer by layer. The net shapes are same. It is important that we create properties of both the parts which are subtractively and additively manufactured as the same. That's when the actual technology can be used. There are various processes to go into additive manufacturing, including plastic and metal. So there is fused deposition modeling and stereolithography, laminated object manufacturing, and inkjet printing, which can also be used as one of the technologies, or maybe electron beam melting and selective laser sintering or selective laser melting, as it is called. So with all of these technologies in plastic and metals, you need to be using the proper technology which is most suitable for the part and the function. Because if you are only wanting the part to give you a ergonomic shape and size and fit and function, then you can go for a low-tech FDM technology. But if you want the part to also function into the field, you need to use what is called a selective laser melting or SLS or direct metal printing as one of the technologies which are there. So it finds various applications, and the technologies themselves coming into different raw materials, such as, to begin with, if you have a liquid material or a resin or a powdered material or solid material to begin with various transformation methodologies such as polymer curing or heat being used for solidifying, adhesion and laser being used into various technologies such as VAT polymerization or DLP, direct light projection, or metal jetting, powder bed fusion, binder jetting, material extrusion, and sheet lamination, into the common names like SLA, which is stereolithography, direct light projection, or multi-jet printing and polyjet printing, color jet printing, and FDM and LOM. So this one slide gives you the various technologies in 3D printing. They can range from, we have ourselves seen machines coming into on a tabletop as at the cost as low as 75 to 80,000 rupees. And then we ourselves have implemented machines which can be as high as, let's say, 12 crores and 13 crores of rupees into large organizations, where we can even print flying objects going into the satellite or maybe going into the tools that we manufacture. So the technologies are widespread. The application needs to be the key while deciding this. And as I said, 3D printing finds applications into healthcare, dental applications, aerospace applications, which could be even engine parts of the aerospace. And believe it or not, the flight that you are taking next time, you will realize when I'm talking about that the engine that that is firing for the aircraft to fly already has a lot of additive manufactured parts fitted into it. Automotive design or automotive customization. And then, of course, there are lifestyle products such as durable goods and shoe soles and even mobile covers and things like that. So a whole spectrum of industries can come across additive manufacturing. Talking about virtual reality, it has also started becoming lighter by the day. So good old days, we used to have a virtual reality room, which you can see at the bottom right corner, where you have something like a screen and a room where you can walk around, and people with goggles on their heads. This has now been translated into a place where we can, in fact, fire a meeting request the way we are meeting today here using Microsoft Teams. We could fire a meeting using the link and wear goggles and sit on chairs and actually see a part like this seated across geographies, and that can give you a strong message into e-learning. Despite being separated by each other by geography, you can actually be able to learn how things actually work It can be used for training manuals and things like that. You can have design reviews for teams across locations, product and maintenance training, demos, and it can be used as a virtual exposition for parts and machines at the same time. So I'm just touching base these technologies just to let you know. All of you have already had an exposure to this sometime during your working life. But then I'm just trying to make sure that these are the technologies that help you to make a product more robust and the design process much easier. At the same time, more functional in a sense that the products are becoming more and more reliable and durable in their sense. I'm going to demonstrate to you through a few videos. So let us take laptop as the part of the product design. And here you can see a CAD being used where the design and simulation of the product will happen in front of you. We are trying to make sure that the products, you can see the hinges of the laptops were designed here. And once you have the product physicality designed and the features made, you go into what is called as a simulation. And here we are doing the physical simulation first. So you have all of these parts together. You are putting stresses onto it, making sure that these stresses are within the blue and green ribbon, as you can see, and nothing is red. Even if it is red, it is in control, and you have methodologies to make sure that these are. I talked about having heated components because of the radio frequency, and then you needing a fan or something to cool it down. So you are also taking care of that. On the next, we are going to talk about making the product possible virtually and making the designs change basis the virtual simulation that we just saw. And then we are adding a few what you can say lures to make sure that the cooling is better. Then we go into the actual electronic simulation of the part and see all of the chips and the semiconductors on the part being simulated for the entire electronic design. And all of this being done using electronic simulation as one of the parts. Then you go into cooling. So you have the entire development, validation, managing the entire embedded software. So we started off with the physical appearance of the machine. Then we went into the physical simulation. We went into the flow simulation because of the heat which is created. We created methods to make sure that the cooling happens in the time. And then, of course, the electronic simulation to give you the entire signal integrity and making sure that whatever function that you had to make. So next time when you are working on a laptop or a mobile phone and you realize that it has gone slow or maybe it is heating too much, and it is affecting the performance, you know now why it is being done, because the product is not properly simulated. And then that simulation can happen and give you a very confident looking part. And that's where the cost of part can increase, where the R&D, as we say, the research and development goes behind the physical simulation, the flow simulation, the electromagnetic simulation, which is all in all together called as the multi-physics simulation, which can be summarized into these simulation domains such as the structural simulation, the thermal, multi-body dynamic, motional and dynamic simulation, safety simulation, flow simulation, acoustics, and vibration simulation. Acoustics is all about vibration. Material simulation. We are working with a company which gives additive manufacturing software, and we can change the alloying in that and make sure that the part can be changed very fast. And we get the material simulation, the durability of the product, as well as the electromagnetics that we just saw. So with all of these various domains of simulation and the CAD, the combination of these two has made the product design very, very confident and robust. So with this, I come to the end of the first chapter, which is called as the digital twin of the product. And this digital twin of the product is something that is actually the virtual prototype, or you can say the twin of the physical element that we see on the hands of people. So at this point, I am just assuming that this is all something that you already knew, but I am just trying to brush your knowledge. And with this, if there are any questions at this point, I can take one or two and then go into the next chapter.
Sir, we will take the questions at the last.
Fantastic.
We do have questions, but we will take it at the last.
Fantastic. Let me go into the second part, which is called as the process simulation. And once you have the product designed, simulated, virtually tested, prototyped, now confident enough that this part is good to go into mass production, we go into the process. And this process can start off by, first of all, tool design. That tool design can start with the various processes. May it be manufactured on a machine, which could be a general purpose machine or a special purpose machine. It could be used, there can be a forming process, a non-cutting process that is, or it could be a cutting process. And then for that process, we need to simulate the process to make sure that the part which we had started off to design is also being able to be manufactured effectively on the shop floor. So we have the complete control on the process as well. While talking about the tool design, which of course is my core subject of importance, being a student of tool design myself, and starting from cutting tools, jigs and fixtures, press tools for sheet metal components, injection molds and blow molds, compression molds for thermostats, and die casting dies for non-ferrous alloys, are all coming under the umbrella of tool design, one of the processes for making mass-produced parts. Then we have machinery. As I talked about general purpose machines, we talked about the milling machines, the lathe machines, and I'm going to cover a little bit of that again to brush up knowledge. And I'm very sure that all of this coming together is only going to instigate a few brains here and make sure that we link it to the process. And that's where I come from, which is the plant simulation or the process simulation, which is something which I would like your attention to. All of these coming to the second part of this chapter, which is called as the process development. And in the process development, as I said, let me go back to the basics and go to the cutting tools. And I am sure all of you can relate to these with the turning tools or the grinding wheels here, milling tools here, various types of end mills and horizontal mills being used into either vertical or the horizontal machines. So these are the tools, these are the machines on which they are used. You can see a lathe machine, a tool and cutter grinder, a horizontal grinding machine for surface grinding. And all of these machines you have all seen on the shop floor. The unfortunate part here is, like we started off discussing, not only have engineers stopped writing things with their own hands, they have also stopped going into the shop floor. And one of the important aspects of my, I can say, profile has been to make sure that core competencies such as mechanical, electrical, electronics, or civil engineers are sticking to their core competencies to begin with, because very easily we get drifted into the IT world and you go into a space where people do not compare with your background or educational skill sets. So if you are a little bit resilient into these technologies, I urge all of the mechanical engineers, electrical engineers, and electronics engineers to be into their core fields to begin with, and make sure they associate with these topics to begin with, because IT is irrespective. It is actually agnostic of any of the core competencies. But if you stay with the core competency, your future shall be much better. You can see here use of technology. A virtual reality technology being used to assess the methods of creating a press tool. So here we have created a virtual training class for educating how a press tool works. So you can see these are all CAD tools, but they have been mechanized here. You can see the entire clamping and declamping and injection cycle of a injection molding cycle. So when coming from the cutting tools and the standard general purpose machinery, these are also now becoming standard machineries such as the metal presses and injection molding machines, which are creating plastic as well as sheet metal parts. And then we go into the tool design processes to make sure that these are properly simulated. Here you can see, for example, a flow simulation of an injection mold, where starting from the gate of the injection mold, you are filling into a part. And you can see here that the entire flow simulation is being done. For a plastic part here on the second image, it's for an aluminum part, or maybe a forged part, as you can see here on the right top, or for a sheet metal part on the top. These are all simulations of the processes that you are going to take into account for mass producing the products that you have designed earlier. And these process simulation are one of the first beginning of your simulation world. We also go into machines or special purpose machines, which can now have mechatronic concept designer. As you know, the entire machine is not only mechanical structure. It can also have wires going from one place to the other. There are a lot of wiring, routing, which are there. There is embedded chips and software included into this. So all of these together make a machine, and that machine is now becoming a mechatronic assembly by itself. And this mechatronic assembly will first have a basic 3D geometry. It will have sensors and actuators at various parts, which are created into the bill of material here. Then there is a reference destinations of these parts. There is force, loads, and all of that profiles created into this. You have control signals which can talk about how and where these parts are going to move. Then the entire cinematic description, the way you're seeing here in a dynamic manner, design of cam plates and things like that, and the sequence of the machine. All of this finally comes into a chip or a PLC, which needs to be programmed. And the best part today with such tools which are available in Mechatronics Concept Designer. So as I told you, while the processes of cutting tools and special purpose or general purpose machines remain the same, we need to adapt to it with various technologies such as Mechatronics Concept Designer and a few more technologies that we're going to talk about into this section to make sure that you know now that there are technologies available to allow the entire kinematics and the simulation of the entire machine to give you a PLC code, which will finally be running onto the actual machine. So here again, without even investing into a single screw, we are simulating virtually the entire machine operation, creating a PLC program, making sure that that machine is virtually commissioned in front of you, and that virtually commissioned machine is now ready to go into the design or shop floor. So this entire process, we are going to see how that happens, and this is going through the Mechatronic Concept Designer. I can show you one of these machine concept being designed. So when you say concept, this is a vial filling machine concept for a pharmaceutical company, where the concept of how to develop the vials with a moving slide and various injectors coming into play. I'll play this image again, this movie again, to show you that a concept level, a CAD level concept has to be converted into an actual process. And this process can now be virtually tested on your screen. Plus the software behind it, the electrical and electronics behind it can also be tested, and a PLC program can be created out of this machine. So you can see this machine, the earlier stage, you saw that only a segment of that machine was there. The entire machine now is engineered into a PLC code generation through a TIA portal, which is the totally integrated automation portal, and connecting to a PLC programmer through a virtual mode. So let us be clear here. We are still not talking about the shop floor. We are still continuing to talk about this virtually on a computer of course, a little bit higher capacity, and creating a program level for the machine that we just conceptualized. Here we go into the twinning, a process twinning, where you validate the PLC code with the virtual world. So you have a machine which was physically virtually tested here. I'll play this again. So you have this machine concept being tested, the dynamics being shown here, and then we have a digital twin, such as a Simatic S7 1500, which is a PLC from Siemens, and this goes into the development of the entire. So you do the cell validation, you have the entire robotic validation, you can even have a human validated, and all of that to give you what is called as the cycle time throughput, build quality, safety, reach and clearance, because all of these multiple arms working together so near to each other can conflict their paths with each other. All of this can be regulated and planned in such a manner that you give the maximum and optimum production cycle and that cycle can itself be simulated for pick and place, welding as well as assembling parts onto the shop floor. Again, I repeat, all of this is still on the virtual mode, which is commissioned in front of you in the screens. Here we can see a material flow optimization into an entire factory. So an entire greenfield factory can be modeled like what you are seeing on the screen, and that modeling can actually be put to simulation. This simulation can help you reduce the stock size, can give you the entire flow of the material, give you the aisle sizes, the material handling equipment requirements, giving you the dimensions of the entire factory, the flow of the material coming inside the stores, and finished goods being rolled out from there into loading trucks. And all of this together simulated in one single environment, which is called as the plant simulation. I have a few videos again here, and the same mechanism which we just started by saying the laptop. And we are now putting the laptop, which was designed and simulated virtually, into the production simulation. So we are now creating the various parts into the laptop and their manufacturing processes. So we are selecting those parts and designing a process to manufacture it. So you can see how the manufacturing design is getting connected to the process that we are going forward. And then if there are any human assemblies required, you can see how a person who is assembling these can be put into simulation, which is called as a human simulation. This is just a small laptop, but imagine that this was a larger, a larger shop floor where heavy parts are being used. You can even simulate whether it is possible for the person to actually pick up the part, whether or not that process will put some neck pain, some lumbar pain into a person. What model you can see here can be simulated for various geographies. So we know that Europeans are a little bit more strongly and more heighted in their overall makeup, whereas the Oriental people are a little bit shorter, and so their hands can't reach where the Europeans' hands can reach and things like that. I'll run this again to let you see that the person changes colors. So primarily it is about the stress that person is going through. The way a physical, a virtual product is put to stress after such an activity that this lady is doing in front of us is repeated over the entire day for, let's say, 200 times, 800 times. How much of that person is going to be stressed, and whether or not this fits into the entire industrial design thing is also becoming a part of the norm into industry. So not only the processes which are there, which are robotic in nature, but even human intervention which is required into manufacturing can now be simulated using these technologies. We now go into the entire simulation process of a robot. So you see that even before the parts are actually on the shop floor, they can be simulated using virtual robotics and checked whether the laptop which was designed by us and the reachability of that is complete with the robotic arms which are going to assemble these. So all the entire process being simulated here, the process simulation happens virtually again. And this way we know the stock sizes, what are the speeds, what is the cell timing, and all of the industrial engineering things can also be done so that we can actually come out with a throughput simulation of the entire part. From there, we go into the entire factory simulation, and we put the entire line, so simulate the entire production process itself by creating an entire factory structure. You can put material movement here, the truck movement and things like that, where the entire cells of the entire factory can be simulated. Going forward, you can automatically generate PLC codes via the totally integrated automation. You can just pick that whole process and put here to be able to combine that with a virtual PLC, and then make sure that the software is in loop, and then finally the hardware also comes into loop. So the software in loop and hardware in loop concept of the process digital twin is something which I would like to show here again. And that's how the PLC coding happens. The digital twin of the process connects with the motion here of the already programmed robot. Once that is done, then it converts into a PLC code, and then that physical code that goes into the physical layout. So you saw the virtual thing earlier going into the physical world, and that's where the software, which is the virtual commissioning and the physical commissioning, are now linking things together. So that's how, as I said, the importance of process simulation, plant simulation, cell simulation are going to be very important in the days to come. I'll show this again. You can see here the screen, and this screen is actually of a robotic simulated cell where it's getting converted from a virtual computer to a physical world, where the SIMATIC S7-1500 is now connected with the robot, and then that's how the programming, which was validated virtually, is being tested physically as well. And you create a process digital twin through this methodology. So we move on from the product digital twin, which was the first part, to the digital twin of a process, or the production digital twin, and that's where we come to the third chapter, which is the performance or digital twin here. And the third chapter of this discussion, which was primarily coming from the performance monitoring and improvement process, primarily coming from what is called as a smart factory or a connected factory, taking care of Industry 4.0. So Industry 4.0, though I come from the industry of Industry 4.0, I must say that Industry 4.0 itself is a little bit of jargonous application. What we all saw until now, the digital twin of the product, the digital twin of the process, and now we are going to see the digital twin of the performance monitoring. All of these also are segments of Industry 4.0. So it is not necessary that we adopt to it completely. We can also take smaller steps into adopting of this Industry 4.0. And when we talk about this, we are talking about the first, second, third, and the fourth industrial revolution, which started way back. So we know about the French Revolution, which started here, and the industrial revolution using steam engines, going into the use of electrical. Mr. Sachin at the start showed about these. Then the third was the industrial revolution using automation, and then here you have the cyber physical system, where you have controlled programs and connected factories, like we are going to see from here. So the complexity has increased, and we now see here a typical shop floor, which has got a production execution scheduling being done. This scheduling is actually based on the schedule that you have received from your customer, and slowly but surely the entire process is being mapped in such a manner that you get an automated schedule in front of you. This can be used for at the planning level, where the work instructions can also happen electronically. And once you have the entire process designed, you can create work instructions and give those onto the shop floor in a connected manner, so that you have the entire value chain from the product design to process design and manufacturing connected together in a single environment. You go into manufacturing execution system for discrete element, where these machines which are being used for production are also evaluated for their performance, and each of the machine gives you their overall equipment efficiency, and make sure that you create such charts for giving an automated information which can be intelligently, I can say, evaluated, to make sure that whatever process plan which was created in the second phase of our discussion comes true into the shop floor, and create a digital twin of performance as well. So here you can see an efficient use of the TIA portal, where this is a vision camera which is being used for the production, and here SIMATIC, SIMNumeric, SIMMotion, and all of these technologies are there coming from Siemens, being put to use for actually making sure that we are fully connected. So all of this, what you are seeing on the screen, is completely connected to the initial part of the product as well as process, going back to the shop floor, and the shop floor fully connected with PLCs, the TIA portal, which is the totally integrated automation connected together. And already virtually it has been commissioned. Now you are physically going to machine parts, and here you can see a CNC controller for turning application being connected to the part. Then you go into what is called as the cloud-based Internet of Things, which includes the operating system. So you have the initial design and the entire process, which is connected through all of the digital information transfer. MindSphere is just a name here, which is used by Siemens for the industrial IoT, and then it is connected to the factory so that all the applications and the information flow, the intelligence that is going to be available to the management and the supervisors at the shop floor are completely being monitored. And all of this coming together in one single instance, which is into a connected factory. This is how the factory of tomorrow would look like. I'm going to also play a video very soon, which will talk about how the industrial IoT will enable manufacturers to connect their entire factory and the internet to give data and the analytics. So when you say data, analytics comes along with it, and that analytics can help us make your processes much better and futuristic. You can analyze these data which is being created for predictive maintenance. For example, when you have continuous information coming from your shop floor, and leave aside the all the jazz behind this, what you just saw. But let's say there is a motor, and that motor has a bearing at the end which is connecting to a shaft, and we are having a sensor at that particular point which is giving us the temperature of that bearing. Imagine a point where the temperature is continuously showing an enhanced temperature for over the past 1 week. It's just like what we are doing. So I'm wearing a wearable device here, and I'm using it to track my heart rate. In normal days, if I were to be having a good night's sleep, or having a good exercise in the morning, my routine being maintained, and then I am not dwelling too much into too much of activity during the day, and not abusing myself in the evenings. What you can get as at the end of the day is a cycle, and that cycle can be repeated. Now imagine a place where you have the motor bearing increased in temperature. So you know that the grease inside the temperature has either melted down, or you need to replace that, or a predictive maintenance is to be done. So such information outlets coming from the shop floor through such connected factories can help you do the predictive maintenance. You can also do process optimization, where you can use this technology with the information that you have got to make sure that the entire process optimization also happens. You can also use this to optimize your resources, for that matter. For example, you now know exactly how many number of people are required to use this, what is the kind of power required for this, what is the kind of other resources which are required. And you can extend this process optimization into other facilities such as the people, the tools, and the material which are there around it. You can also use this technology for energy usage and savings. So electrical energy is a big commodity to be used today, and this is very expensive for a factory to run, and a saving in that can help you to do a lot of optimization into your power consumptions. All of this coming together into information. So you have a repeated technology. Just to give you the same example that we just talked about, I go on a morning walk every day, and I used to also run at times. So when you are running, you start your exercise routine and you start running or walking, and it gives you automated signals saying that you have now completed a kilometer and your heart rate is such and things like that. Can you imagine today? I may forget to put this on, and I just start walking. And after about 10 minutes, it tells me that a kilometer is now completed. So are you walking? Are you into the exercise? It gives me a vibration giving me a reason to put yes, that I had forgotten to put my exercise routine on. But it has intelligently taken into account that I have started walking, and after about 8 to 10 minutes, when I'm about to complete a kilometer, it is reminding me that if you are trying to walk now, you should have probably put my exercise routine on. So such artificial intelligence or machine learning exercise exercises can also be possible once you have such instructions in place. And then all of these can be captured together to give you deep learning, and a little bit more of that can be discussed in detail into, as I said, various segments coming forward. I'm going to run a video again, which is going to talk about the entire smart factory connection.
When it comes to digitalization, the world is moving faster than ever before. We like, we swipe, we stream, we share, no matter where, no matter when. But digitalization is not only affecting our personal lives. Entire business and job models are changing. Industries are evolving towards a new era, and companies that don't adapt will simply vanish. This transformation is driven by smart products in a purely digital process called smart manufacturing. But whose factories are smart today? How can a manufacturer become faster, more agile and efficient without excessive costs? MOM, the Manufacturing Operations Management System, is the answer. MOM is essential for smart manufacturing to create a digital twin of operations that is perfectly integrated with automation and the real factory. It is the digital brain in the manufacturing space, understanding the goals of the smart product, using abstraction techniques to link to shop floor devices, and making them even smarter. The resources required for each smart product are optimally allocated by the MOM scheduling system. And the MOM execution engine guides the smart product through the factory, interacting with automation, operators, and logistics, guaranteeing high quality and enhancing manufacturing efficiency. All data coming from the shop floor is collected by MOM and contextualized with detailed manufacturing information. Using closed-loop manufacturing and quality, MOM fills the gaps between execution, product engineering, and production planning, enabling continuous improvements of your factory and seamless new product introductions.
So with this, I'm almost about the end of the discussion which I had to do today about the digitization. And we started off with the digital twin of the product, coming to the digital twin of the production, and then going into the digital twin of the performance. And all of these three connected together into a single environment, giving a feedback loop coming from all of these together into each other, so that we know that there is a continuous improvement which is going to happen into the product design, into the process, as well as the performance. So this is all what I had to talk about the entire digital enterprise. I had thought this to be a little bit more interactive. I will invite questions, and I think I've just taken about 60 minutes to actually do the talk. But I would definitely want the next 20 minutes to be as interactive as possible to make sure that we come to a place where we understand where this thought process has gone. And I'm just hoping that this discussion, which started in the sense that in this way, the way I have presented, was useful and giving you more information, because I'm very sure talking to students is a little bit of difference than talking to professors and lecturers that I am doing today. But at the same time, I thought let this be just a brush up of the information at least, and come up with these compilation of information which is already there into the domain, to be able to connect you through these three things of product, process, and performance. So with this, I again thank you, Ullash Dada, to be my, what you can say, inspiration to be into this session. And I'm just hoping that this session until now has been useful, and you've been able to get some more information that you already did not have. Thank you very much again. I take questions now.
Thank you so much, sir. We are sure that your session will be useful for students to pursue their journey in smart factories. Now I request Professor Rameshwar Chavan for questions. Thank you, sir.
Yes, am I audible, sir? Good afternoon, sir.
Yes, yeah, good afternoon. Good afternoon.
Sir, we have some questions asked by students and faculty members. First question is by HOD Mechanical Engineering Department, Professor PG Taur. In today's era of digitalization, how students are trained and in which specific technologies?
So we started off by a prologue where we had Dr. Ullas talking about the curriculum not being upgraded to the speed at which technologies are getting upgraded into the factory, and the factory is reporting that the fact that the students are not employable immediately because they need to be trained. So in my opinion, what needs to be done is a combination of these two things. One is an industry and academia partnership where you understand from the industries which come to recruit people from your college to understand their needs. And then those needs are a part of your curriculum is something that you should adopt to. We would be more than pleased to be able to help to you into making this possible.
Okay, thank you, sir. Next question is from SY Mechanical Engineering student, Aniruddha.
Yeah.
What is the difference between Industry 4.0 and IoT?
So IoT is a part of, it's a subset of Industry 4.0. If that explains. So Industry 4.0 is a larger, encompassing many technologies together into a connected factory. I don't want to use jargons here. So if you go by definition, so I'm sure we remember, all of us remember the film called as Three Idiots, where the professor asked what is a machine, and then there is a bookish explanation of what that machine is. And I'm sure if you go to the web and see what Industry 4.0 means, you'll have the definition there. But IoT is a subset of Industry 4.0 because it encompasses a larger connected factory environment as well as the design of the product, the performance, and the process together into a closed-knit environment. IoT is just a part of that.
Okay, sir. Next question is from Harsh Sharma, sir. Can you please suggest a way by which students can integrate their domain mechanical engineering knowledge with the new programming languages or IT skills, and which makes a great career out of it? As we are observing nowadays, there is a major shift of mechanical engineering graduates toward IT, as they are trying to learn programming languages for getting higher paying jobs, and they are making a good career in ML and AI.
Yeah, so this is one of my favorite topics, and excuse me for a little bit longer answer to this. First of all, you talked about better jobs, and let me tell you, better jobs are something that is only for the engineer, the mechanical engineer, to start off with going into the IT, because he gets a higher pay package probably. And you can imagine large companies, I don't want to name any of them, coming and taking people by thousands per year. So I hear one of the top companies is going to recruit 53,000 fresh engineers this year. So you can imagine that what they're trying to do is they're already trying to use a methodology of the 12th standard, what you can say, filter, which was created, that those who have done with good grades, coming from a better background in families who can pay the fees, are the people they want to recruit, so that then they can be groomed to do programming. Now, coming to the core skills. So if you were to be able to use your mechanical engineering or electrical engineering or electronics engineering, I have already showed you various tools which can themselves be learned. And let me tell you, we have, for example, a set of employees, some of them masters in their courses, doing simulation design. Some of them are doing fluid. We are doing projects for the Government of India, Department of Space, Department of Atomic Energy, Department of Space, as well as DRDO labs. We are working for Serum Institute. We are working for various such organizations where we need people from core engineering background which can understand what has this tool. So if I were to answer your question, the IT skills which we are talking about are not programming languages. The IT skills is the knowledge about simulation, knowledge about CAD, knowledge about process simulation, all of the tools which I have just shown. irrespective of the discipline that you come from. So even if you are from mechanical engineering, electrical engineering, electronics engineering, there will be tools within your umbrella which you need to learn to be able to get better jobs. And should I tell you that once you get into this domain, the greener pasture that you're talking about, the higher jobs or highly paid jobs into the IT, just about 2 to 3 years of investment by doing this core subject matter IT programs, you will see that your career is riding much faster than IT engineers. And when I say IT engineers, we're talking about programmers. Notwithstanding that, there can be other things such as people not liking to be a mechanical engineer because they were pushed into mechanical engineering because they got good marks or because their parents wanted there. Then in that case, of course, you have a reason to go into IT. In that case, I would definitely want you to be aware about the latest technologies such as Python, or that matter any programming, because once you have the algorithm or your brains ready for coding, you can actually learn many things. Python as well as data analytics tools such as Tableau are tools which are very skill oriented and job oriented.
Okay, thank you, sir. Next question is from HOD Electronics Department.
Yes, sir.
Rajesh, Dr. RM Audi, sir. Specifically for ENTC branch students, what basic skills to be adopted from first year engineering to final year engineering, and please focus on project-based learning to get more knowledge.
Perfect. I'm a mechanical engineer and I have come into this industry. I've been into this industry for about 32 years now. And I see more and more reason for electronics engineers to be a part of this manufacturing boom. What needs to be inculcated into the curriculum is the low frequency and high frequency simulation, magnetic simulation, electromagnetic simulation, which is there, because that's a very vast subject. From there, you come into a boom of electrical vehicles where there is battery management, the entire connected vehicle technology which is coming. So we just saw of connected factory, but a vehicle which is going to come from tomorrow. And with all of these pandemics and wars around us, I'm sure that we are also going towards some self-sufficiency if we have some electric and electronic design engineers. Let me tell you that India is at a cusp of a boom of semiconductor industry. $300 billion is the size of industry that is going to come up in the next 10 years. So no better time than today to be electronic engineers in India. And a few years back, electronics engineers were only doing that because they wanted to go into the IT. But if they remain into the core business of electronics and semiconductors, I am sure there will be several such opportunities coming up. We see Apple and such companies tying up with Tata now, where all the variables of Apple will be manufactured in all, meaning a bulk of their manufacturing will happen in India. And all of these employing electrical engineers, electronics engineers, wanting to do the core design and simulation in India. So I think what you need to learn from beginning is design and simulation for electronics. We need a lot of people into these core domains, and we don't get such people. Let me tell you that also, that a lot of electrical vehicles are being designed across the country, and they need a lot of people into electrical, electromagnetic, electrical, electronics, as well as semiconductor designs. And we don't get such people. We find that these are more interested in to go to IT, which is the programming languages, rather than the core electronics. Okay, thank you, sir. Next question is from Computer Science Department faculty member, that is Sugandha Nandedkar. Can you please focus more on MOM related to computer science, message oriented middleware? Come again, please. Can you please focus more on MOM related to computer science? Computer science. So yeah, obviously. So when we talk about all of these technologies together, ma'am, we're talking about manufacturing operations management and manufacturing intelligence, which happens through, let's say, industrial Internet of Things, or the Industry 4.0 technologies that we just saw. All of these will be connected together. So when we say connected, it is not only the design process and performance, it is also the connectivity with the enterprise software. So we have ERP being running into a company, and that ERP could be SAP, Oracle, or any other thing. It could be having a database, which could be SQL or Oracle, and there could be programming languages which are connecting all of these enterprise along with the manufacturing operations. So there are 3 or 4 buses which can, if you like, that can happen into the company. So all of these connected software can be connected together in the form of a life cycle management software, which is called as a PLM. There can be an enterprise software, which is an ERP, and on the shop floor we have got manufacturing operations management. For an IT or a computer engineer, there is a huge opportunity of connecting all of these 3 together, in the sense that we have integration of these 3 buses together as a great need into the industry today.
Okay, thank you, sir. Next question is from mechanical engineering faculty members Vishal Sahare.
Yeah.
What is the role of mechanical engineering in IT company?
What is the role of mechanical engineering in IT company? In my opinion, there is no role. And sorry to be a little bit blunt, but if the IT company is working for a mechanical engineering company as a customer, then the role of a mechanical engineering in an IT company can be the functional expert to begin with. So, for example, if the IT company is working with the banking sector, or if it is working with retail, for example, I don't think a mechanical engineering engineer has any role. But if the IT company is working for manufacturing operation management of a manufacturing company, let's say Procter and Gamble. I know for sure that TCS, for example, is an IT company, known as an IT company, but its engineering division, which works for, let's say, P&G and its plants, which are connected together, is having a mechanical engineering on board because he understands the function of the manufacturing. So the role of a mechanical engineer in an IT company can at the best be functional, or being able to design the architecture of the entire product, not coding at all.
Sir, thank you, sir. Our director, sir, wants to ask you one question.
Sure.
Sure, sir.
Ajay, it was a really nice lecture. I attended it completely.
Thank you.
And
Thank
now
you.
there will be 2 parts. One is the 3D printing, 3D manufacturing, and last is the IoT, or we can say Industry 4.0.
Yeah.
Now, particularly, there's a good opportunity for the engineers to become entrepreneurs with the 3D technologies.
Yes.
So what should be the prerequisite that we should make change in our syllabus, that students will get a thorough knowledge of 3D printing?
This is a very good question, Ullas, that you have asked. Let me tell you, after working into industry for 30 odd years, or maybe, and I have come across people who have worked for 10 years, 20 years, 15 years, the way they have studied design is always towards technologies which are manufacturing processes which are subtractive in nature. So when we talk about a design and its manufacturing process, even while designing, we think subtractive manufacturing as the technology which is going to manufacture the product that we are designing. What happens is there is a lot of unlearning. So I am just giving you a small example that if you are driving in the country in India for all these ages, and you go venture into European nations and go to Germany and want to hire a car, you will have to unlearn a lot of things of the right hand drive and then learn to do the left hand drive. So this unlearning which I am talking about is to be done by people who have been into industry for a lot of time. If the people if the students are still into their curriculum, they need not unlearn because they have not learned anything in that sense. So what you need to design in a part of the curriculum is what is called as design for additive manufacturing. When I say design for additive manufacturing, let me explain this a little bit more. That many often times what happens is people make a mistake by saying that, okay, they show me a part, say, give me a part and say, okay, this is the part which we are making today. And how much will it cost making into additive manufacturing? This is a very wrong example or a wrong comparison, in the sense that whatever is being manufactured subtractively can continue to be manufactured subtractively for ages. What needs to be additively manufactured is to be redesigned. So there has to be a course which talks about design for additive manufacturing, because by designing for additive manufacturing, and let me take a little bit of time. Okay, let's do it sometime later. But just to tell you that let's say a part which can be whose topology can be optimized in such a manner that it does not have any limitation to manufacture. Can I take a few moments more here?
Yeah, surely.
Okay. Just give me a second. I'm opening another presentation which I just recently gave, and which very much addresses this question. Yeah. So let me share my screen again here. So this is a presentation I recently did to a CEO of a large company, where you can see that a part which is on your right is being shown here, and this part has multiple flows. You can imagine that such a part which would not have been designed earlier, because such a methodology to produce such a part will not be available in the world today. So how to design a part which can be additively manufactured to give you a reimagination of designs by expanding its product performance. And when I say performance, let me go a few slides later. By reducing its weight, if this part was a flying object, let me tell you that something which is going to be a part of a flying object, let's say an aeroplane or a satellite launcher for that matter, you can imagine that a single kg or a few grams of reduction in the weight of a material can actually result into thousands of euros saving, primarily because the fuel that will be required to be carried by the satellite launcher will be much more lesser because the light weighting of this part. So let me give you examples of this part. So this is a lattice structure you can see here inside, and there is a part which is having a geometry outside, which has got a lattice structure inside, which is making it hollow. The part is fully functional. It is having the same strength as the normal part, but it is lightweight to an extent that it is only 40% of the total weight. Now, to design such a part, traditionally designers will not think of this. They will have to learn how to design for additive manufacturing. There are other parts, for example, here, there is a traditional part, a bracket here that you see, has been converted into a geometry which is topologically optimized here. And this topologically optimized part is something that cannot be manufactured using traditional manufacturing methods. It can only be manufactured using additive manufacturing. So design for additive manufacturing is something that should come into picture. I'll go to one last example here, and this will explain you furthermore. Is there are some 13 parts into this burner assembly. So there are 13 machine parts joined together with 18 different welds to make this part. Now these 13 parts which are joined together with 18 different welds has been combined together to create a single 3D printed part. And this single 3D printed part is 1 kg less. It is delivered in 3 weeks as opposed to 26 weeks. And it is now having a better performance. So this would not have been possible if you had thought traditionally. It is only possible if you have known how to design for additive manufacturing. Does that explain, sir?
Yeah, thank you, Ajay.
Thank you. Most welcome.
Sachin, now we can wind up. Or some more questions are there?
Unmute Venagil. Unmute Venagil.
Any more questions, Sachin?
Just wait, sir.
I see Mr. Jivan Salunke here.
He might be with your batch, Jivan.
Exactly. Yeah, that's why. But I don't see his image here. This is muted as well. And
Jivan, please on your camera.
I think yes, it's.
Jivan, are you there?
Sound sir को phone करो. Sound के sir. Okay. जाओ sir गए sir.
Hello.
Sir आगे.
Yes sir, I am there.
Hi, hello.
How are you?
Fine,
thank you.
Good to see you. I saw your name and I must say that this is the same Jivan which I know.
Yeah. How are you, Ajay?
I'm fantastic. Thanks for having me here today. I'm hoping that this session was useful to all of you.
Yeah, definitely. Particularly for the students also, it is definitely useful.
Great.
Now, Ajay, we'll be having one MOU. Whenever you are in Aurangabad, you are going to visit Devgiri.
Okay.
Yes. Okay, thank you.
Thank you so much. Thank you so much for this invitation. Thanking for your attention and time. Thank you all. Hoping that you had some information additionally coming to you from this session, and looking forward for more interactions in the future. Goodbye and thank you.
Thank you so much, sir.
Thank you.
Now I would like to request Professor Javed sir to give vote of thanks.
Thank you, Chavan sir. I, Professor J.B. Sheikh, feel immense pleasure to express vote of thanks for this inspired talk. I am beyond grateful to Mr. Ajay Deshkar for getting us through the concept of product, process, performance, digitization. He covered complete lifecycle process and technologies used in modern days, adopting Industry 4.0 techniques of connected or smart factories. Thank you for taking the time to do this. Thank you to Mr. Sachin Chitanand and Rishikesh.
म्यूट झालात सर तुम्ही.
Javed sir, mute झालात तुम्ही.
You are muted.
Okay, sorry sir for this technical problem.
Okay.
I am beyond grateful to Mr. Ajay Deshkar for getting us through the concept of product, process and performance digitization. He covered complete lifecycle process and technologies used in modern days industries, adopting Industry 4.0 techniques of connected or smart factories. Thank you for taking the time to do this. Thank you, Mr. Sachin Chitanand and Rishikesh Kolapkar from 3D Engineering Automation LLP Pune for their participation in this session. My sincere thanks to our patron, Shri Prakash Solanke, President, Marathwada Shikshan Prasarak Mandal, Shri Sheikh Ahmed Sheikh Salim, Vice President, MSPM, Shri Satish Chavan, Secretary, MSPM, and all management for their support and encouragement to conduct such activities at DIMS. I am so grateful to Dr. Ullas Shurkar sir for his motivational support for the session. I am much obliged to Professor P.G. Taur sir, Head of Mechanical Engineering Department, from his continuous support, help and guidance for the successful conduction of the session. I extend my gratitude toward Head of Department and faculty members of Mechanical, Computer Science and Engineering, and Electronics and Telecommunication Engineering for their cooperation and participation. I am thankful to organizing committee member Professor Deepak Gopekar, Dr. Sachin Agarwal, and Rameshwar Chavan for this program. I acknowledge the effort of Mr. Irfan Sayyed, network engineer, for the broadcasting this event live on YouTube. We appreciate the valuable participation of dear students for this technical session. With the permission of speaker and director, sir, I declare the program is over. Thank you, one and all. Thank you. The feedback link is posted in the chat box. Kindly submit your responses. Thank you, sir.
Thank you.
Thank you.
you, sir.
Thank you, sir.
Okay.